The mass-luminosity relationship stands as one of the most fundamental and consequential correlations in stellar astrophysics, establishing a robust mathematical connection between a star's mass and its energy output. This relationship follows a power law where a star's luminosity increases dramatically with its mass, approximately to the 3.5 power for typical main-sequence stars. First noted by astronomer Jakob Carl Ernst Hahn, this relationship has profound implications for understanding stellar evolution, determining the masses of distant stars, and predicting stellar lifespans. The relationship is particularly powerful for main-sequence stars, but becomes more complex for evolved stars like giants and supergiants. The physical basis lies in how increased mass creates higher core temperatures and pressures, accelerating nuclear fusion processes. Through decades of careful observations of binary star systems and theoretical modeling, astronomers have refined this relationship, revealing subtle variations across different stellar mass ranges that provide crucial insights into the internal structure and energy transport mechanisms operating within stars. The mass-luminosity relationship is mathematically expressed as a power law, where a star's luminosity relative to the sun's luminosity is proportional to its mass relative to the sun's mass raised to a power. The physical basis for this relationship lies in the fundamental processes of stellar physics. Higher mass stars have stronger gravitational forces, leading to greater compression of their core material. This compression results in higher central temperatures and densities, dramatically accelerating the rate of nuclear fusion reactions that generate the star's energy output. The mass-luminosity relationship was first identified by Jakob Carl Ernst Hahn and has since been refined through extensive observations of binary star systems. Binary systems provide the most direct method for determining stellar masses through orbital mechanics, allowing astronomers to establish empirical relationships between directly measured masses and observed luminosities. Significant empirical evidence comes from studies of close binary stars in the solar neighborhood, which demonstrate a strong correlation between mass and luminosity for main-sequence stars. These observations have been compiled into comprehensive datasets, such as the work by Torres et al., which analyzed 190 binary stars with well-determined parameters to construct accurate mass-luminosity relations. These empirical studies reveal not only the general trend but also the natural scatter in the relationship, which provides valuable information about stellar evolution and compositional differences. Although the mass-luminosity relation follows a general power law, the precise value of the exponent varies across different ranges of stellar masses, reflecting changes in the internal physics of stars. For main-sequence stars with masses between 2 and 55 times that of the Sun, the commonly used exponent is approximately 3.5. However, for lower mass stars, where convection becomes the dominant energy transport mechanism, the relationship changes significantly. In these low-mass stars, the exponent in the mass-luminosity relation decreases, reflecting their different internal structure and energy generation processes. At the other extreme, for very massive stars exceeding 55 solar masses, the relationship flattens to become nearly linear, although such massive stars are inherently unstable and rapidly lose mass through intense stellar winds. The transition in the power law exponent reflects fundamental changes in stellar energy transport mechanisms, from radiative transport in higher mass stars to convective transport in lower mass stars. The variation in the mass-luminosity relation across different stellar masses can be largely attributed to changes in how energy is transported from the stellar core to the surface. In stars more massive than about 1.5 solar masses, energy is primarily transported through radiation, while in less massive stars, convection plays a more dominant role. This difference in energy transport has a profound effect on the internal temperature structure and consequently on the luminosity of the star. For stars burning hydrogen through the proton-proton chain, which dominates in lower mass stars, theoretical models based on homology relations predict a relationship where luminosity scales with mass to approximately the third power. In contrast, more massive stars primarily burn hydrogen through the CNO cycle, resulting in a different scaling relationship. The transition between these different nuclear burning processes further contributes to the variations seen in the mass-luminosity relation across the stellar mass spectrum. The mass-luminosity relationship, while robust for main-sequence stars of similar age and composition, shows notable scatter when examining a diverse population of stars. At each mass value, there exists a spread in luminosity that exceeds observational error margins. This variation is attributed to two primary factors: differences in chemical composition and evolutionary effects. Stars with different metallicities have slightly different internal opacities, affecting how efficiently radiation can travel through the stellar interior and ultimately influencing the star's luminosity. Additionally, even while on the main sequence, stars gradually evolve as they convert hydrogen to helium in their cores, causing subtle changes in their luminosity over time. These evolutionary effects become more pronounced as stars age on the main sequence, contributing to the natural scatter observed in empirical mass-luminosity relations. The influence of rotation and stellar winds. Beyond mass, composition, and evolutionary stage, additional factors such as stellar rotation and stellar winds can significantly influence a star's luminosity. Rapidly rotating stars experience centrifugal forces that slightly alter their internal pressure balance, potentially affecting their luminosity output. This effect becomes particularly important for massive, rapidly rotating stars. Similarly, stellar winds, which are flows of gas ejected from a star's surface, can be substantial in high-mass stars, resulting in mass loss over time. This ongoing mass loss affects the star's evolution and consequently its position relative to the standard mass-luminosity relation. These factors introduce additional complexity to the mass-luminosity relationship, particularly for massive stars, where both rotation and stellar winds tend to be more significant than in lower mass stars like our Sun. Beyond the main sequence. Application to evolved stars. The mass-luminosity relationship becomes significantly more complex when applied to stars that have evolved off the main sequence. Giant and supergiant stars, having exhausted the hydrogen in their cores, undergo substantial structural changes that dramatically alter their luminosities. These evolved stars typically have much larger radii and higher luminosities than main sequence stars of equivalent mass, placing them in different regions of the Hertzsprung-Russell diagram. The mass-luminosity relation derived for main sequence stars, therefore cannot be directly applied to these evolved stellar objects. For giants and supergiants, the luminosity depends not only on the star's mass, but also critically on its evolutionary stage, with core and shell burning processes creating distinct luminosity patterns. While mass remains a fundamental parameter influencing these stars' properties, the relationship becomes more nuanced and requires more sophisticated models that account for their complex internal structures. White dwarfs and compact objects. At the extreme end of stellar evolution, compact objects such as white dwarfs represent a complete departure from the main sequence mass-luminosity relationship. White dwarfs, being the remnant cores of low to intermediate mass stars, have a completely different internal structure governed by electron degeneracy pressure rather than thermal pressure. Consequently, they follow an inverse mass-luminosity relation, where more massive white dwarfs are actually smaller, and for white dwarfs of similar age, often less luminous. This inversion occurs because white dwarfs generate no new energy through nuclear fusion, but rather slowly radiate away their residual thermal energy. The mass-luminosity relationship completely breaks down for other compact objects like neutron stars and black holes, which operate under entirely different physical principles. These exceptions highlight the limitations of the mass-luminosity relation and emphasize that it primarily applies to stars in the hydrogen-burning phase of their evolution. Related stellar relationships. The mass-radius connection. Closely related to the mass-luminosity relationship is the mass-radius relationship, which describes how a star's size varies with its mass. For main-sequence stars burning hydrogen via the proton-proton chain, with energy generation parameter V4, the radius scales approximately as m/37. For more massive stars burning hydrogen predominantly through the CNO cycle, with V17, the radius scales approximately as m/16/20. This relationship reveals that more massive stars are not only more luminous, but also larger in radius, though the scaling is less dramatic than for luminosity. An interesting consequence of these scaling relationships is that more massive stars have lower average densities despite their greater mass. These interrelated scaling laws between mass, radius, and luminosity form a coherent picture of stellar structure across the main sequence and provide important constraints for theoretical models of stellar evolution. From mass to temperature. The HR diagram. The combination of the mass-luminosity and mass-radius relationships allows astronomers to derive a theoretical relationship between luminosity and effective temperature, which defines a star's position on the Hertzsprung-Russell HR diagram. For stars burning hydrogen via the proton-proton chain, this relationship approximates to log L, 5.6 log Tef plus C, while for stars burning hydrogen via the CNO cycle, it becomes log L, 8.6 log Tef plus C. These relationships predict a double power law slope for the main sequence on the HR diagram, which aligns well with observational data. The mass of a star thus serves as the primary determinant of its position along the main sequence of the HR diagram, with more massive stars occupying the upper left region, hot, luminous, and less massive stars residing in the lower right region, cool, dim. This fundamental connection between mass and a star's observable properties makes the mass-luminosity relationship a cornerstone of stellar astrophysics. Applications in modern astrophysics. Determining masses of distant stars. One of the most valuable practical applications of the mass-luminosity relationship is its use in determining the masses of stars that cannot be directly measured through binary orbital dynamics. For the vast majority of stars that are either single or in visual binaries without well-determined orbits, the mass-luminosity relation provides the most reliable method for estimating stellar masses. By measuring a star's luminosity, derived from its apparent brightness and distance, and assuming it lies on the main sequence, astronomers can use the inverse of the mass-luminosity relation to estimate the star's mass. This technique has been essential for building comprehensive catalogs of stellar masses and understanding the mass distribution of stars throughout our galaxy. The relationship is particularly useful when studying stellar populations in distant clusters or galaxies, where individual stellar masses cannot be directly measured but luminosities can be determined. The mass-luminosity relationship has profound implications for understanding stellar evolution and lifespans. Since a star's luminosity determines how quickly it consumes its nuclear fuel, and this luminosity scales steeply with mass, the relationship directly informs predictions of stellar lifetimes. More massive stars, with their disproportionately higher luminosities, burn through their hydrogen fuel at dramatically faster rates than lower mass stars. For instance, a star with twice the Sun's mass will consume its fuel roughly 11 times faster, significantly reducing its main sequence lifespan. This inverse relationship between mass and stellar lifetime explains why massive, luminous stars are relatively rare, despite their high visibility. Their extreme luminosity comes at the cost of drastically shortened lives. The mass-luminosity relation thus provides a quantitative foundation for understanding the age distribution of stellar populations and the chemical enrichment history of galaxies through successive generations of stars. The mass-luminosity relationship stands as one of the most fundamental correlations in stellar astrophysics, providing a powerful connection between a star's most basic physical property, its mass, and its most observable characteristic, its luminosity. This relationship, expressed as a power law, where luminosity scales approximately with mass to the 3.5 power for typical main sequence stars, has far-reaching implications across numerous areas of astronomy. While primarily applicable to main sequence stars, with important variations across different mass ranges reflecting changes in internal energy transport mechanisms, the relationship forms the foundation for understanding stellar structure and evolution. The scatter observed in empirical mass-luminosity relations reveals the subtle influences of stellar composition, age, rotation, and mass loss, adding richness to our understanding of stellar physics. Through its applications in determining stellar masses, predicting evolutionary pathways, and interpreting stellar populations, The mass-luminosity relationship continues to serve as an essential tool for astronomers seeking to unravel the complexities of stars throughout the universe. As observational techniques improve and theoretical models advance, our understanding of this crucial relationship will continue to deepen, providing ever more precise insights into the lives and deaths of the stars that populate our cosmos.